Well, welcome, and let's look at section 6.2 this morning. Definite integrals. We will be reviewing um, really the definite integral and how to compute it on a calculator. And this is one thing that we haven't done for a while. How do you do a summation? And evaluate the sum is what it says. We see we have the summation from 1 to 4 and of n squared. So I think because it is such a short interval, our index starts at 1, finishes at 4, that I'm just going to do it by listing each of the terms of the series out. So when 1 goes in, I start with n being 1. I'm going to have 1 squared plus. Next step, n will be 2. 2 gets squared. Next step, 3 steps up, or n steps to 3. I get 3 squared. And lastly, we are at n equals 4, and I notice stop because I hit the top number. Then I'm just going to sum 1 plus 4 plus 9 plus 16, 10 plus 20 equals 30. Next one, let's just do a listing again. There's only going to be 4 terms. This time they're using k as their index. So that doesn't make it any harder, just using a different variable. So we start with k being 1. We have 3 times 1 is 3 plus 1 gives us 4. Added with, now k steps to 2. 2 times 3 is 6. 6 plus 1 gives us 7. Next one, 3. 3 times 3 is 9, plus 1 more is 10. And finally, we are at the top number. We know this is our last term. We would have 12 plus 1, giving us 13. We got 20. 20 plus 10 is 30. I'm getting 34. Okay? Write the sum in sigma notation. And it looks to me like we are just changing by ones. And we're stopping at 50. We're starting at k equals 2. So I'm going to do a summation from k equals 2. Stop at 50. And basically, it's just going to be k. Okay? And then the next time k steps up will be plus 3, then plus 4, plus 5. That should work. The next one looks like if I multiply by 2, no, can't multiply by 2. What if I add by 2? Yeah, there's the pattern. Okay, let's start at 2. K equals 2, and I'm going to add 2 to that. So k, I was going to say k plus 2, but then k is going to step to 3, isn't it? And then I'm going to get 5. So I've got to think of a way to keep things even. So if I did 2 times k, then I would get nothing but even numbers. And that seems like a pretty good approach. And let's back down then and start k at 1. So I get 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. That seems to be the pattern. If k is 50, I would get out my 100, and there is that pattern. I've got 3 times some number to the third. 2 looks to me like we're just increasing this number by 1. So let's say we have the integral, I'll use n this time, n equals 1, and that's going to be a 3 times n to the third, and we need to stop once we reach 100. So some nice easy patterns to work with on that one, not so bad. All right, quick review. We did all those. We should be fine. You know the definite integral of a continuous function on a to b is a function that's going to be partitioned out from x equals a to x equals b. And it says let f be continuous on the closed interval a to b, and let a to b be partitioned into n subintervals of equal length, where that we can calculate the width of our intervals, saying delta x is equal to b minus a divided by n. Then the definite integral of f over a to b is given by the limit as n goes to infinity of the sum from k equals 1 to n of f sub k times delta x, where each c sub k is arbitrarily chosen in the kth subinterval. So, kth subinterval, because we know we're summing up kind of infinite number of intervals, we remember that this is really calculating the height of a rectangle, and this, of course, is a width. When they said that kth where c sub k is chosen arbitrarily, what they're saying is it's neither left, right, mid. We can't really predict. C sub k could be anywhere along that kth subinterval. So they're just showing that possibility of c sub k coming from anywhere. And let's just write this. Definite integral is the limit as n goes to infinity of k equals 1 to n summation of f sub c sub k times delta x. And the existence of definite integrals, all continuous functions are integrable. That is, if a function f is continuous on a to b, then its definite integral over a to b exists. We just need continuity of the function. So, terminology. Leibniz's clever choice of notation for the derivative dy dx had the advantage of identifying very much like a fraction in both the numerator and the denominator. Although not really fractions, the derivatives can behave like fractions, so the notation makes profound use of the chain rule. So if I had a couple different functions and maybe I had y's and u's in it, and maybe I had one function that had x written in terms of u, I could take the derivative with respect to u, and let's say this with respect to u, and by multiplying these individual equations together, I can get the du canceling and come out with an answer of dy dx. I feel like we saw that maybe in one of those AP worksheets we did recently, where you could have taken this approach. So just that was a nice little thing on Leibniz notation. Now, the interval, negative 2 to 4, is partitioned into n subintervals of equal length. Let m sub k denote the midpoint of the kth subinterval and express the limit as, in this case, as an integral. So, if my limit is going to infinity of n, and I'm summing up, then I know that this really represents an integral. And this integral would look like my bounds would be, how do I want to do my bounds? Oh, they told us, negative 2 to 4. And my function, well, this is going to represent the height, and this here is our width. So I'm going to just say that I've got 3x squared minus 2x plus 5. The width is taken care of by the differential x, because this means very, very small x, infinitesimally small. The next one, oh, I guess they wanted me to put, it's not a different problem, is it? They want me to put that right there. Number 2, same idea. N is going to infinity. I've got a summation going on from k equals 1 up to infinity. I have some c sub k selected in my stretch between x sub 1 and x sub 2. They've chosen some c sub k in the kth subinterval. So let's just convert this into an integral on the bounds -7 to 5 of x squared minus 3x dx for our width. These really are pretty easy to convert. This is not bad at all, is it? Next one, width and height. So my function would be represented right there. This would be the integral from 1 to 4 of 1 over x times dx. And lastly, we are on this interval from -pi to +pi of sine cubed of x dx. We did this last year, and I always think this is worth going through because it just reminds us, what does an integral represent? Well, one of the things it represents is the accumulated area, the area under the curve. So this says if y equals f of x is a non-negative and integrable function over a closed interval, a to b, then the area under the curve, y equals f of x, from a to b is the integral of f from a to b. So I know that I can calculate the area under the function y equals x. And if I did this, I could just throw on the equation y equals x, and I want to go from 0 out to b. And now what I want to do is capture this area under the curve. So it is a triangle, and we know triangles are calculated as 1/2 base times height. My height, when I have b, this point here will be b comma b, because I put it into my function there. And my width, my delta x here, will be b minus 0. So that would give me b, or the base area. So I'd have 1/2 the base times the height. So it looks like we have 1/2 b squared as the answer to problem 23. What about problem 26? Why don't you hit pause, see if you can do it yourself. All right. I would sketch this line. We got f of x equals 3t. It gets locked at the right when I hit b. It doesn't start till a, and it tells me that a is larger than 0, so I know I'm to the right. The region that I want to calculate is all this region. And to me, that looks like a trapezoid. So I'm going to calculate it like it's a trapezoid. And my calculation is going to be, I need to know the height on each of these, and I need to know this distance. Well, this distance is easy. This is just b minus a, isn't it? And for this point here, when I put a in, I get a comma 3a. And when I put this b in, I get b comma 3b. So now I know the distance along here is 3b, and this segment has a length of 3a, and now I should be able to say the area under the curve is equal to 1/2 b minus a, height on the left, plus the height on the right. Number 30. What is it asking us to do? Find the output. Oops. Did I skip ahead too? Where did I end up going? This is where I want to be, isn't it? For some reason, that's the one I skipped over, isn't it? The integral of a constant. This one people do have problems with. If f of x equals c, where c is a constant on the interval a to b, then the integral from a to b of f of x is equal to, well, we said this is going to be a constant, is equal to c times dx. And that can be calculated just by going c times b minus a. And you can see over here, we've got this constant function at y equals c, and if I'm capturing the area from a to b, then this distance is b minus a, and the height is c. So it's just a rectangle under the curve. So number 7, evaluate the integral. Well, we have a height of 5, and it's going to run from -2 to +1, and we're looking for this region. The distance on the x-axis is going to be 1 minus -2, which would be 3 units, and it is 5 units high, so this will be a 3, you know what, I'm going to do it like they had done up there, a 5 and a 1 minus -2 equals 5 times a 3, so we get 15. Pi over 2, 3.14 divided by 2, this would be like around 1.5-ish. Y equals pi over 2 is our horizontal line. It is stretching from -4 to -1. This is the region that we're interested in. So the area of this curve, well, this distance we know is -1 minus -4. Looks like the distance is 3 units, and it's pi over 2 high. So height times width, b minus a, says that we've got pi over 2 times 3, or 3 pi over 2. Now, there's the one I jumped ahead on, but that's okay. It really didn't impact us too badly. And then we get this question here. I'm just looking ahead because I cannot find that in my notes. I'm wondering if this was, oh, I do want to do that with you. Okay. So let's back up and let's go ahead and go through this. Multiple choice, 2 to 5, f of x dx equals 18. Then what happens, this is some of those properties of integrals. So what happens if I go f of x plus 4? Well, this would be a vertical shift, wouldn't it? A vertical shift up by 4, which essentially builds us a rectangle that is 4 units high, and we tag that on to the result of 18. So I would be picking up, 3 units here, a 3 by 4 rectangle, so I'm picking up 12 units. This would turn out to be 18 plus 12, giving us 30. You could use properties and break this into a 2 to 5 f of x dx plus a 2 to 5 of 4 dx. that would be allowed to. And then we just got to get that calculation, which we showed. It's a constant function, so it's b minus a times the constant. 46, which of the following quantities would not be represented by the definite integral from 0 to 8, 0 to 8 of 70? So we know that this is like 70 times 8 minus 0 for an area. The distance traveled by a train moving 70 miles per hour for 8 minutes. Ooh, miles per hour. It's the hours and the minutes that are kind of messing me up there. That seems like that could potentially be the wrong one. But I'm going to read through the rest of them. The volume of ice cream produced by a machine making 70 gallons per hour for 8 hours. That's okay. Because remember, typically inside the integral is what we're integrating is a derivative. So when they're talking about gallons per hour, that's the rate of the derivative function. And then this expresses the amount of time that elapses, the x-axis for the t. The length of a track left by a snail traveling 70 centimeters per hour for 8 hours. I think that's fine. The total sales of a company selling $70 of merchandise per hour for 8 hours seems fine. The amount the tide has risen 8 minutes after low tide, if it rises at 70 millimeters per minute, millimeters, minutes, that seems fine. It's got to be A, where we have that mismatch of units, time units. So essentially what this would have been doing was saying we had 0 to 8, where this was in minutes, and then we were trying to integrate miles per hour dt. What would the dt be? Would it be minutes or would it be hours? There needs to be a conversion done there. So enough on that. Not sure why I have that there, but we're going to go into, oh yeah, I do know why, because the next one deals with it. We know that this is the sine function, and then this is the cosine function. They have a phase shift by that amount, and 2 units on this scale is a pi over 2. So cosine and sine have this phase shift going on, where cosine is phase shifted by pi over 2 to the right. Let's see. Find the integrals of the signed areas. And here we go. I'm missing something, and that is the definition, and maybe it's located, I know it's located on your sheet, on your worksheet, it's just not showing up there. This is what I'm looking for, right there. That should be brought up, because we have to have a starting value or put it in the calculator to get what the area of something is for sine x. So this is telling us from 0 to pi, sine of x dx is 2. So what is the area pi to 2 pi? Well, I know for sine, it looks like this, right? 2 pi, pi, and 0. So if this has a region of 2, then this would have a region of negative 2. So we know if it's underneath the x-axis, it's negative. From 0 to 2 pi, it would be 0. Now, what type of function is sine? Odd or even? Sine is an odd function, and therefore it has some symmetry above and below the x-axis. Also has symmetry, it has symmetry over the y-axis, and in this case, we are also seeing that symmetry above and below the x-axis here. All right, here would be the symmetry over the y-axis. Now, 0 to pi over 2. 0 to pi over 2 looks like it cuts it exactly in half. So we're just making use of a lot of geometric properties. What happens on this one? Well, this would be like saying I've got the 0 to pi of 2 dx plus 0 to pi of sine x dx. This is a constant. It has a height of 2 and a width of 0 to pi. So I would calculate this out as 2 and pi minus 0. So we're getting 2 pi for area there, plus this one was already defined for us. It was 2, so I'm plussing 2. Looks like I have 2 pi plus 2. Sine of 2 sine x. Well, this changes the amplitude, doesn't it? That would change amplitude. So now it's going twice as high, twice as low. I could, by the properties of integrals, bring that 2 out front. And then I could say I have 2 times the value 2, the area under the curve. So I get 4. And that does make sense. It was amplitude was doubled, so it doubles the area. Now, when I look at 6, this is a horizontal shift, isn't it? This is a horizontal shift to the right. But when I look at, which makes this a little bit tough, but when I look at the bounds also got picked up and moved to the right by 2 units. So we're really still looking at the same quantity. So this just gets lifted and moved by 2 units. So I still have the units residing underneath that first loop. So I think this shifts by 2 as well. So everything still stays completely untouched. 2 units under the curve. If I go negative pi to pi, well, I know the shape of my curve. I'm going to have a negative 2 and a positive 2. This will zero out. This changes the period of the sine, and it makes it go twice. B would be equal to 1/2. And you took the period of sine and divided it by b. So now I'm stretching this out to 4 pi. So it takes it twice as long to complete one cycle. So 4 pi, it stretches it out by doubling it. We will get 2 times 2. We'll get 4 units there. And cosine from 0 to pi. The answer on that one, oh, that's the one I always have trouble with. I think it's 1 unit. Because you're going to cosine, I got too many things drawn here. So here we have sine. And cosine picks up a phase shift by 1/2 a unit. So cosine starts up there and comes down like that. And they want us to go 0 to pi. So 0 to pi, it would be hitting -1. That could be 0 units then, couldn't it? Because you'd have above and below being equal. I thought the answer was 1. Check that in your calculator. I think 9 is definitely the toughest one out of all of them. All right. I'm going to try and come up with a webassign to take the place of this old my math lab one. But I definitely want you, I think this is in your notes. Yes, it is. I want you to do these problems based on knowing that. We know what about x cubed? We know that it is an odd function. So somewhat like the sine curve, we know odd function, and it looks something like this. Think of your areas under the curve would be in that region. Okay? Good luck with 47 through 56, and then we'll try to get an online assignment as well. Good day.